theorem says is the theorem says the following. If you take a 90-degree triangle like that, so you are given the fact that this is a 90-degree angle, and then you draw what we call the altitude of the triangle. Now, the altitude of the triangle, we can also refer to it as the height of the triangle. Got it? But I specifically draw a height from that 90-degree vertex. So I drop the height down from that 90-degree vertex, so this is also 90 degrees. Then I actually now have three triangles that I've formed. The first triangle is triangle A, B, C, the big triangle, the original one. Then by drawing in that height from the 90-degree vertex, I've got another 90-degree triangle, which we'll call triangle ABD. And I have another 90-degree triangle, which we'll call triangle ADC. Now, because we are busy with similarity at the moment, what do you think happens always when I take a 90-degree triangle and I drop down that height? What will always happen with these three triangles? They will be similar. They will be similar, absolutely. So that means triangle ABD, triangle ADC, and triangle BAC will be similar. And we'll quickly just prove it. You don't have to, because according to this theorem, you can then just go and you can make the statement. So the reason that triangle ABD and the big one, triangle ABC, are similar is, number one, you've got a common angle at B. So that's a common angle. Then over here, because we've specifically gone and we've dropped down a height, we know that is a 90-degree angle. So we know that angle BAC, I should rather put the smaller one here first, sorry, because I wrote it in this particular order. So I have to first state the small one's angles. So angle D1 is equal to angle BAC, which is 90 degrees, and that is pretty much from my construction. Got it? Because I constructed that height down. So that's from my construction. And then lastly, we have angle A1 up top there, which will then be equal to angle C. And that's just going to be sum of angles for triangle. Now, that means that triangle ABD is similar to triangle, so A to B to D, so C to B to A. So this is actually in the wrong order, sorry. ABD, CBA. Because of angle, angle, angle. And then I can do pretty much exactly the same thing with the other small triangle and the big triangle. So I can just say, similarly, not going to do the whole thing again. Triangle and this order, let's just write this down. And I just want to keep the order the same. So that means we know in this triangle over here, angle C is going to be common. So if I put C first there, I have to put C first there. Then the 90-degree angle there is at angle A. So that means I have to put D there, which means the missing one is then going to be C to A to D. So similarly, those two triangles are also similar. That's horrible to say. Similarly, those two triangles are also similar, but that's pretty much what it is. So I can then eventually go and I can say this. because ABD is similar to CBA, and because CAD is similar to CBA, I can make the statement that all three triangles are similar to each other. Got it. Now, the interesting thing that this does is the fact that those three triangles are similar actually allows you to prove the theorem of Pythagoras. You go, what? It does? Really? How? Well, by using all of these little bounces. Do you understand? So the theorem of Pythagoras, you will recall, says that BC squared, which is the hypotenuse, is going to be equal to AB squared plus AC squared. You agree with that? So I just need to go, and in this statement over there, I need to find all of those sides. I need to find all of those little bouncy bounces. Okay. And by the way, it's not necessary to do because they've never, ever, ever required this proof. So I don't actually want to do the part. You can if you really desperately want and you want to see it. Okay, I will show it to you, and I'll show you how using similarity can actually prove the theorem of Pythagoras. But I don't really care about proving the theorem of Pythagoras. I just care about the fact that this is a very useful shortcut. Because this is a theorem, the moment they give me a diagram like that, like this, do I really have to go through this whole process to make this statement? No. I can jump straight to this statement in one go. And the reason I'm going to use, let me just confirm that this is the correct reason, because like I said, they never ask it. So because they never ask it, I can never remember it. It's the truth. Have you ever noticed if you never ever use something, you never ever remember it? There. The reason for it, so you can just jump straight to this one, and the reason for it will be perpendicular from the 90-degree angle to the hypotenuse. So that's a very fancy reason, but it's pretty much saying if I draw a perpendicular line from the 90-degree vertex onto the hypotenuse, then I can make that statement immediately. I do not have to go through that whole process of proving this. So I can just literally, if I get this diagram, this one, I can immediately jump from here to there, which is a lovely shortcut. If you see anything like this in the exam, gorgeous shortcut to use. And that's pretty much all of the Euclidean geometry content. Okay. Thank you so much for listening.